Okay. Yeah, I need to set up the VGA port, and my X server crashed all the time, so I have now another card. But seems to work, yeah. Okay. I'm gonna talk about Miracast on Linux and what I did in the last half year to implement it and to make it possible. Miracast is basically HDMI over IP and that over Wi-Fi. It's not like DLNA and other media streaming things which are really centered around files or which have seeking and allow you like horrible UIs where you select the file and do stuff. Miracast actually is just to get your screen from one device into another one. And it defines a source, and a sink source obviously is a device that creates an image, whatever it does to do that. And a sink is a device that displays the image, usually a TV or a monitor. The connection, the new thing about this is actually that it uses Wi-Fi peer-to-peer. I want to first explain what all these words mean, so everyone knows them. The 802.11 specs are the official Wi-Fi specs, and they define how Wi-Fi works. And then there's the Wifi-Alliance, which creates some common practice specifications which define things on top of these Wi-Fi specs. And there's one spec that's called Wi-Fi peer-to-peer. I think that's 6 years old now, I'm not sure. And Wi-Fi Direct is the certification program name of the Wifi-Alliance, but it's basically the same. And in 2012 they released the Wifi-Display specification, which defines Miracast. Miracast is again just a fancy name. It's the certification program of the Wifi-Alliance. I'm always trying to use peer-to-peer and Wifi-Display, so I hope you don't get confused by that. Okay. The first problem I had is that all these specifications from the Wifi-Alliance are not free. You have to pay for them, but apparently you can just Google for them, you can find them. Okay, let's first look at how Miracast and Wifi-Display work. The architecture is you first have two devices which have to discover each other, and you have to set up the peer-to-peer transport. On top of that, you create an IP link, so you have to use your IP network from one peer to the other one, and then it's just use your TCP, UDP to get your audio-video transmission. It's quite simple, and they try to reuse as many known protocols as possible. I want to go through each of these steps and just explain how they work, how I try to implement them. Yeah. So for transport, we have three things. We have device enumeration and discovery. We have negotiation and connection establishment, and we have the IP link setup. Sounds straightforward. Apparently, it's not. It took me 4 months to get this working. It was this Monday that I got the first Wi-Fi device working.
You're just not very fast.
Yeah. Let's start with enumeration. The Wi-Fi peer-to-peer standard defines how that works, and you simply have two devices with a Wi-Fi card, and they send beacons so they can find each other, and you use the normal Wi-Fi scan to find other devices. The problem now is you need to know whether it's peer-to-peer capable and obviously whether it's Miracast capable. So what Wi-Fi peer-to-peer uses and what Wifi-Display uses is informational elements which you can put into different frames in the Wi-Fi specs and Wi-Fi action frames and beacon frames and so on, which define whether you support Miracast, whether you don't, what resolutions you support, and so on. And this way you can filter devices, you can directly see whether, if you found one, whether it's a Miracast device or not, which is quite handy and you need that. On the other hand, they define like a whole lot of information that you can put in there. As I said, supported audio modes, supported video modes, supported resolutions, and so on. So it's bloated and huge. You have to code like a lot to get it working. And I don't see why, because you do the exact same thing once you have a TCP connection. But okay, that actually works quite nice on nearly all Linux machines which can do peer-to-peer. The problem with negotiation. The peer-to-peer standard uses action frames for two devices. One device connects to another one. The peer-to-peer standard defines action frames to do group operator negotiation. That means one of two devices needs to create a soft AP, and the other one connects to this AP, but you don't know which device does this. So you have this three-way handshake, which also works quite nice. And yeah, then the one side creates an AP and you connect to it. And again, you mark the AP with information elements, so other Wi-Fi clients will not try to connect to it. The Wifi-Display standard actually allows peer-to-peer and TDLS, but peer-to-peer is mandatory, and I haven't seen anyone using TDLS or supporting it. TDLS means tunnel direct link setup. They have two devices which are connected to the same access point, and they can create a direct link by routing their messages to set up this link through this access point. On top of that, once you have this usual IP setup, you use WPS and WPA2 like on every other network. Once you get your Wi-Fi connection, you can create an IP link, and we have just two devices. So what you could do I just pressed right and left. Anyway, what we could do is just IPv6. You do network discovery. There are just two devices, so you know who the other guy is, and it's not working. You just, well, can send commands. But apparently that's too hard, so we don't do that. What we do is with a network with two clients, and you use DHCP and IPv4, which is awful. Especially if you know the DHCP server implementations, which we have as open source, are horrible to use in an ad hoc mode where you just want, on one link, you want to spawn it, pass it a prefix. It just doesn't work, so I had to actually get the command implementation out there and rewrite it to do it like just short. The other problem is IPv4, obviously, is quite narrow namespace, and they normally use 192.168, and if you're unlucky, two networks you're connected to just use the same address. You have no chance to avoid that. Yeah, apparently IPv6 is quite a new technology, which is not ready to be used. But one of the remarks is that it supports stereoscopic 3D, which is like probably 10 years older than IPv6, but don't IPv6. Yeah, I don't know. They just screwed it up. Anyway, I got it working too, and so it's fine. So now we have a link setup, and Wi-Fi P2P should just work. But obviously, we still have a problem because it's not that easy. It depends on the drivers on Linux, and I need to implement peer-to-peer. A lot of drivers just cannot support it because the firmware doesn't allow these interfaces, and these are like the old ones and the Broadcom one, and yeah, I have a lot of devices at home, tested these all, and then I tried first looking what chipset the device has and then buying it and testing it, and then I crept through the kernel sources and tried to figure out which drivers support it. Quite a few. claimed to support it. So I went ahead and bought these devices. First I started with USB devices, and they didn't work. It just failed. Then I bought an Intel card, because I thought Intel works quite a lot on that, but it didn't work either. Then I brought like 200 messages to the Wi-Fi development list, and they probably didn't care, I don't know. One guy, after pinging 3 times, helped me to like track down a bug, and so I got one setup working. This is an Intel card with a 7060 card, which is a PCIe card, so you cannot easily plug it. And you need the supplicant revision, which I posted there, because everything newer is just broken. And I tell them, and never got a response. Awesome. So if anyone of you thinks they can go home and use it, you can't. Sorry. Anyway, I was working on this was transport setup, and that works. It's stupid, but what can we do? On top of that, we now have the other part of the Wi-Fi-Display specification, which defines, once you have an IP network, how to transport your data. And what it does is basically RTSP, RTP, plus MPEG-4 plus audio, and puts it into an MPEG-2 transport stream, which is, if any of you work with that, is quite common and works on Linux. And once I got, after 4 months on Monday, the connection setup working, it took me 2 hours to use GStreamer to get the other stuff working.
Did you publish
GStreamers? Sorry?
Did you publish the pipe for GStreamer to get it working?
I can just, no, I haven't written it anywhere, but it's in the Git repository. You can just look at it. And then I thought the demo probably won't work, so I went ahead and just decided that this Wi-Fi-Display specification is quite nice and has a feature I always wanted, but the peer-to-peer stuff is just not working, so I thought, why not just make HDMI, Wi-Fi-Display, but without Wi-Fi, just require an IP network. So you can use the implementation I wrote just over Ethernet, over usual Wi-Fi, whatever you want. So, as probably all people know how RTSP works, RTSP is the main part of this, the control channel that is used for Wi-Fi display. And RTSP is usually used if you have a streaming server and you want access to that server and want, like, request a stream and get the data. But the problem with that is, in Wi-Fi display, usually the source side, the side which produces the data, is the one which initiates the connection. But once you do that, you have the IP set up, you have to wait for the sink to actually connect to the source and say, I want your data. So it's actually reversed, and you pull the data into the sink. And this is so ugly that they implemented, well, the RTSP messages don't allow the source to start streaming if the sink doesn't want the data yet. So they added messages which allow the source to say, trigger play, and they send it to the source, to the sink, and the sink says, oh, I'm supposed to be playing now, and it starts playing. But they use RTSP just because, well, it's known, but they just, yeah. Horrible. Again. Anyway, RTSP is pretty easy. It's HTTP basically, just with different commands. And you can just hardcode that and it works, and that's fine. And once you get the setup working, you do mode negotiation. The sink says which modes are supported. The source selects one of these modes, and you can select the MP4 profile. You can select other modes. Once you have that, you start streaming, and then you use RTP. RTP is used on UDP, and that's just a stream of data from the, well, I guess it's now just data from the source to the sink. And the RTSP stream is not used anymore. You can request mode renegotiation or other stuff, but I haven't seen anyone who supports that. To encode data, MPEG-4 is used, as said. For audio, which you can also optionally transmit, there are AC3, AAC, and some other formats, so anything you want, basically. And then it's put into an MPEG-2 transport stream, so you get reliable transmissions, or rather reliable transmissions. Problem obviously is you need, if you want full HD for that, you need an MPEG-4 encoder, preferably in hardware. The Intel GPUs do that, and it works, but with everything older than Ivy Bridge, I guess it's not working. But I haven't exactly checked that. Decoding works quite nice on slow CPUs. So additional features. The server is done and you have connections between the two devices and can transmit data. Yeah, as I said, I got that working really fast, but there are optional features you can use, like PTP. PTP is used to synchronize the clocks, so that's very important for the last of these features. Which is split sync. Split sync means you have one audio device and one video device, and you send the video only to the video device and the audio only to the audio device, and they are not connected to each other, and you obviously need to sync the clocks between all three, or it won't work. But that's optional too. And then there's HDCP, which is a DRM protection. I won't implement that. There's UIBC, which allows the sync to actually transmit input data back to the source. So you can have a touchscreen on your TV, and you transmit video data, and you touch your TV, and actually can interact. Yeah. And I wanted to share a short demo how that works. As a client, I used Android, but I had that working when I got here, and then I crashed my Android phone, and now it's not working anymore. I'm trying. The nice thing about it is the geo negotiation that you do during Wi-Fi peer-to-peer setup, which means who's the group operator, is rather random. And the Wifi-Display specification mandates that the source has to be the group operator. But if the geo negotiation, as always happens with this driver, just makes the sync the group operator, you cannot do anything. So yeah, I'm just trying this.
Is this supposed to be reliable and working for consumer devices?
Yeah, you can actually, I said it's supposed to be reliable and working. You can set a group operator intent, which means one device doesn't want to be a group operator. Yes, there's many things that you can set, just doesn't work, doesn't do anything. I guess it's again an Intel Wi-Fi problem, but I cannot say. So, working. I actually wanted to show it on the screen, but that's not going to work because my X server crashed when I used WiFi-A. Okay. I'm just putting it in front so you can see it. I hope you got a view of that. That's now an X window where it displayed the data, and that's my Android phone which I connected. And I can show you how the connection works, but that always takes like 10 shell scripts to get working, so I'm not doing that now. One fancy feature that Android has is when you're doing your password input, it doesn't transmit any data, but once you're in your home screen, you can like interact directly to it. It also detects, okay, it doesn't do it in normal mode. Like if you're in the menu directly detects screen rotation and adjusts your screen resolutions, and now you get the white display. It's not centered. Okay. And the most interesting thing, obviously, is like latency for that, throughput, and so on. And Full HD is actually no problem at all. Works quite nice regarding throughput. Latency, obviously, as you might see, is, I would guess, below 100 milliseconds. But I had no chance to get it well, better. But I actually can play games with that, which should show that latency is not as bad as you might think. That's one example game I was just showing, so you can actually see that. So this is now real-time transmission, and I'm not looking on my screen, obviously. Yeah, I'm not that good at it. Yeah, audio doesn't work yet. And yeah, okay, I could do that all day long, but I won't. But it shows that you see screen artifacts if you look closely, and you notice lags, which are in the loop-VA decoder, which I haven't figured out why I get these. But okay. That was one example where you use Linux as a sink, which is quite handy because you can use Raspberry Pi with this mode, and it has a hardware decoder for MPEG-4, and you can just plug it to your TV, get power over USB, and then you have just a Wi-Fi-Display sync at your TV. And that already works, but you need to sit down and spawn the shell scripts in the right order and press your thumbs. Yeah. The other thing, obviously, and that's a much more interesting thing, is to get Linux as a source. And the problem with Linux as a source is that there are many different modes that you can use to produce your data. What you could do is just a file which contains a video, and you want to stream that. Quite easy, but that's not what most people want to do with it. What you usually want is just either clone your desktop or use it as a desktop extension, so it's actually a second monitor. The problem with that is that you have to write an Xorg driver or Western or kernel driver. And because with Wayland we have the problem that every compositor has to do its own will have to write its own driver for that, because it cannot rely on the XOR-based provided driver. So I didn't go with that way. On the other hand, I don't know how to read XOR server code, so I'm quite happy that I didn't have to. But I wrote a kernel driver, which just provides a second GPU, which is just emulated in user space, and yeah. So it's as if you have two GPUs in your card. They provide different displays, but this is just a fake GPU with no hardware acceleration or anyway, but just provides a single frame buffer, a single CRTC, and a single connector, which user space can drive. And then XOR can pick up this card additionally to the usual card you use, and use it as clone mode, use it as separate monitor, whatever it wants. And another process, which is the OpenWFD process I've written, just reads out this data via a character device and pushes it out into via Wi-Fi to the external display. And
would it be possible to use render nodes to have accelerated 3D?
Wait a second. Right here.
The question was whether it's possible to use render nodes to generate that.
Exercise.
The question doesn't really make sense, because the X server does get two cards and it already can do GPU render offloading, so it only uses, it already has a built-in into the card or whatever, and this fake card. And if it renders for the fake card, it can use the other card just fine without render nodes. So it can render on Intel and just offload the data to the, well, it actually can only do that. So, but you could obviously use render nodes in this scenario too. Yeah. Okay, I'm just try to set this demo up, but might be a bit fragile. Yeah, okay. Might take a while. Okay, that one might not be working. Okay. On the list of, would have been nice to see here, but what I got working with that is you can use this, you have a separate interface, and you can use conto-FB map to bind your Linux.
Recipe something. The slide is here.
There's nothing. Very good. But yeah. What I got working is that you can stream the Linux console from one PC to another one. And if you got that working, well, obviously you can get anything working. But that's, yeah, if you write graphics drivers, you know that it's awful to work with a Linux console. And if something works with that, it works with anything. Anyway, back to the topic. I implemented all this in a repository, and as I said, it took me 4 months to get this transport stuff working, which is actually not really part of the Wi-Fi display specification, because it should be just Wi-Fi peer-to-peer, and that should be implemented. At least people claim that it was implemented for long. So I just hacked together the demos this week, and so it's pretty ugly. But I'm reworking that and uploading again and writing blog posts so people know about it. Question is now how to integrate it into distributions or GNOME or other stuff. And the way it works is that we first need Network Manager, Conman or other programs to provide a peer-to-peer API. Before they don't do that, we cannot do anything about it, because you don't want your Wi-Fi display program to control your WPA supplicant, because it needs to issue commands over that. But you usually want to use your normal AP and get internet access, normal network access. And that won't work if the network implementations won't provide that. But if they do, it would be like quite simple. I have 2 programs which you can run. One is a sync, okay, it just accepts data. And the other one, the source one, would just create this fake kernel device. Exert would get a hotline notification, see it, and just use it. So it's just spawning a command, and you could do that easily from any desktop system. Yeah, and that's basically it. I will try to get this demo working again. But if anyone has questions.
Hello, can you hear me?
Yeah.
Yeah, I just wanted to confirm, I think you said about the lagging issues that you traced it to the decoding part. Just confirming that you have ruled out networking and bad Wi-Fi.
Yeah. The latency obviously is for Wi-Fi, but the short hangs you see is even if I do local MPEG-4 decoding.
Okay, thanks.
Yeah. I have one more thing, by the way, before other people ask. There are other implementations. AbbR and Chromecast, both of them actually have a 1-second delay. So, and this is intentional in their protocol. So I don't think that they are really useful for the same stuff. But they're also both closed source, so I'm didn't try to implement them. There is a Linux proof of concept for Chromecast, Aircast, I think, but haven't used that yet. Yeah?
For the kernel side of it, where Linux is a source, how did you implement the
Just a second, just you come with the mic. Let him ask his question first.
Oh, sorry. There's something similar in Samsung TVs, I think, or LG. I tried it with Nexus 4, which is supposed to support Miracast, but it didn't work at all. I just got connected to it, but nothing happened.
You connected to what?
To Samsung TV, I think, or LG. I don't remember.
Yeah, okay. Yeah, I told you about some of the WPA supplicant problems and so on, and I'm not the only one having them. So if you buy products, they have the exact same problems, and you really need to be lucky to get it working. Stuff like the group owner negotiation. So that's actually why I try to split both, to just say I have this one part which does transport setup and the other part which is the Wi-Fi display thing. And now you can create any connection between 2 devices. You can use the soft AP which has worked for years, which works with all these devices, and just connect both and then set up your Wi-Fi display on top of that IP network. but the specification doesn't allow that, so no one implements it, which I think is quite, yeah. But yeah, if you intend to buy products with Miracast support, I wouldn't do that.
So I was just curious about the buffer sharing implementation with Linux as a source, if you had a provision for that so that we avoided copies as much as possible when taking the rendered buffer going over to the network side.
Yeah. I simply memory map that back into the, I need to be obviously independent of the implementation of the real driver which rendered the image. So what I did is I support gem import and get the the DMA buff handle from the real driver, so I have no copy on import in the driver, and then I have one buffer copy there because I would like to just memory map this buffer into user space, and user space can then do whatever it wants with it because it knows, hey, this is the frame buffer, but we're not allowed to do that on DMA buff. You can only do that in the kernel because you have to call CPU beginner access and end access. So I have a super ioctl to just do damage. And then you have handle damage and you just copy the stuff that changed. Actually the same thing that UDL does in DRM. Yeah. What I can do, you can get access to the exact gem handle, and then you can pass it to libva. I don't know whether it supports this. But then you could even do hardware encoding from the frame buffer without doing a single copy. Because otherwise you copy into the frame buffer and you copy again to the GPU to get it encoded.
Hey.
Hi.
How do you handle color space conversion when necessary and scaling of frames, if necessary again?
And what?
Color space conversion and scaling.
Okay. I pass it into GStreamer.
Fair enough.
I actually got a lot of emails from people. I haven't even done any coding yet, and just created a repository and some files. I've got like 4 emails from companies which were working on Wifi-Display, and some of them told me, asked me what my plans are, and I was like, yeah, using GStreamer, and they told me, yeah, it's bad, it's way too slow, and whatever. So was quite amazed this Monday when I got it working. It was really fast. The first one actually had 2-second delay, but then I noticed that I just used it from parameter, and then got it to, well, pretty nice delay, I guess.
I've got a question about the streaming format.
Sorry?
Hello. The streaming format. You mentioned that you're using H.264 over RTP, AAC over RTP. I'm a little bit confused where the MPEG transport stream comes in.
You have an audio and a video stream that both have to be multiplexed over one RTP link.
So, okay.
So
the audio and the video are multiplexed in transport stream, and transport stream is encapsulated in RTP.
Exactly. Yeah.
Okay. Thanks.
Yeah. Yes.
Sorry, could you
1 second, actually.
So my question is just, could you just clarify what AirPlay and Chromecast are? Are they an implementation of Wi-Fi-Display?
Thanks.
So AirPlay and Chromecast, are they implementations of Wi-Fi-Display?
No. AirPlay is one from Apple as a closed specification, and you can, if you're a company, you can get access to it and license it. But AirPlay is actually, I don't know that much about it. I don't think it uses such a good.
Somebody made a port for the Raspberry Pi for AirPlay.
Sorry?
Somebody made a port for the Raspberry Pi for AirPlay. Yeah, it's not official, but it works.
There's Miracast, as I said, someone reverse engineered that. No, that was Chromecast, right? Okay, for AirPlay. It's actually better things like, I heard about it, I've never read it, things like the IPv4 crap, they didn't do, they just use IPv6, I heard, which is really nice, but yeah, can't tell you much about that, sorry. For Chromecast, it's again a different different protocol, it's not the same, it's not compatible, and close source, yeah.
Okay. Do you have some tracks or ID to get Miracast support on HTTP device only? Because some are doing Miracast, but only with encryption, and this is a big trouble for us.
You can implement HTTP. The specification is open, but you need
to buy
a key.
Yeah.
I think you can get access to keys, but it shouldn't be that hard to implement. There might be implementations already.
This is my question.
Yeah, then it should be very easy to use. What you do is basically before you create the RTSP link, you do the HTTP handshake, and that's already it. Would be just hooking into the setup thing. One more shell script in the whatever. That should work. Yeah. But yeah, I don't have any keys, so I can't test, so I won't use it.
Hi.
One second. I just wanted to try the demo one more time. Okay.
Hi. You mentioned the Raspberry Pi earlier, and yeah, I think it's a great device. This would make sense a lot on a Raspberry Pi. So I was wondering if you actually tested those things on a Raspberry Pi or on any other ARM device running Linux, for that matter.
The thing with the Raspberry Pi is that it doesn't have an PCIe, mini PCIe port, so I couldn't use the Intel cards, and all the other cards are broken with Android. But I just used the usual Wi-Fi, simple fake IP, and then got it working. And you can just use it like on any other machine, so it's not special at all. GStreamer, of course, you need the hardware encoding, decoding. And GStreamer has a module called OMX, I think, OS, something like that, which just puts into the pipeline, it's automatically picked up. So, yeah.
Last question, last comment.
I'm curious about the work that you did with the screen mirroring to be able to use Linux as a source. And I know that with Linux right now, there's a really bad problem in the software realm of trying to do live screen sharing or screencasts. Do you think that's something that someone would be able to tear out of there and use it for that purpose?
Screen sharing means
Or like a live screencast. So.